Okay. Welcome to you guys, and welcome to Troels Henriksen, the first speaker at Bornhack this year, talking about his programming language Futhark.
Yes. So I am Troels Henriksen. I am a postdoc at the University of Copenhagen, and I'm here to talk about my pet programming language that constitutes the applied work of my research. But most of the talk will probably be about motivating why we need a new programming language, or actually many new programming languages. So if I ask you to visualize the first computer, you might think it looked like this. But they didn't really. They looked like this. And if you had a very large problem, then it might look like this. And when computers were like this, you really had to think hard about how to distribute your work among all these machines. Because while you could have a lot of them, they were expensive and they didn't work very quickly individually. So you had to split up your work, assign it to each of the computers, and then have some way of combining the results. And that was, of course, very nasty and time-consuming and difficult. So eventually computers did start looking like this, and everyone was much happier, especially because the year after, they looked like this, or some years after. And the code they had written for the first computer, it might have to be rewritten because the high-level languages didn't exist yet, so you were writing everything in machine code, but the algorithms that you were designing were the same. And they ran faster and faster every year, so I could write a language for this machine in maybe in C or Fortran or something, and then 10 years later, I could run that same code or recompile it and run it on this machine, and my program would be much, much faster. And this kept happening for a number of years. Computers kept getting faster, and the code we had written also kept getting faster all the time. We entered the 90s, and then computers started looking like this. But then around 2005, things started to change, and they started looking like this. They still got smaller. Our ability to fabricate microchips still improved, but instead of getting sequentially faster all the time, we just started getting more and more parallel computers, multi-cores. So this is not the end of Moore's law. As we can see, we still have a little while to go before we stop getting more transistors. But on the other hand, increases in sequential performance really started stagnating around 2005. So this world we used to live in, where every year our programs would just get faster without any effort on our part, that stopped 10 years ago, although some people haven't really noticed yet. One consequence of this is, of course, that we get these multi-core CPUs with tens of cores, but we also get much more specialized processors like GPUs, which have a lot of limitations, but can perform a lot of computations for relatively little power usage. Unfortunately, they're difficult to program, and which I will try to explain. So this is a modern GPU. It's not just used for graphics these days, it is also used for general purpose computing. Although it really depends on how you define general purpose. To compare, this shows the difference between a CPU and a GPU. On the CPU here, we have a lot of memory, and we have a lot of cache, and we have a huge control unit, just so these four simple computational units can keep up the illusion of sequential execution. So memory is really, really slow, so we need the cache to try to fake it and make it look like it's faster than it really is. We need this crazy control unit to do out-of-order execution and instruction level parallelism and speculative execution and all that, which of course has some other problems that I won't get into, but are also quite relevant. In comparison, the GPU spends its transistor budget on mostly just on computational units, the things that actually add the numbers or multiplies numbers or do the stuff that we really care about, and has very, very small control units and caches, although it still has the same memory. So as we can see, if one control unit is responsible for a lot of computational units, then those computational units probably have some limitations in how they work. Specifically, within one cycle, all of these computational units have to do the same thing. So branching is more expensive. And I will illustrate that with a programming model called the SIMT model, which is called single instruction, multiple thread. And the idea is that while on a CPU you can have 20 threads or however many that each do completely different things, on a GPU you can have hundreds of thousands or millions of threads, but they each have to do very closely related things. They have to run the same instructions, but in multiple threads. They each have their own registers and such, but they all write to the same memory. Concretely, programming it looks a lot like this. You have a function, there's an increment function, and you say, run this function in 10 million threads, or however many. And then the function goes in, and each thread asks, who am I? And then it gets an answer, and it uses that answer to find some element of an array, increment that element, and then write it back. This is called data parallel programming, where we perform the same operation on different pieces of data. So in this case, we are just incrementing each element of an array by one, and we do this by launching one thread per array element. This would be completely insane in a CPU world where starting a thread and shutting it down is extremely expensive. But on a device like a GPU, threads are extremely cheap and are scheduled on hardware, so there's no context switch overhead when you're switching between threads. On the other hand, each thread individually is quite slow. And even worse, threads can't just do whatever they want. So, for example, if you have a branch in here, you might say, oh, we want to flip every the sign of every negative number in our array. So we have a branch for it. However, because of this SIMT model, where every thread has to run the same instruction in the same clock cycle, all threads enter this branch, even if this condition is false. Only if the condition is false, then they just ignore the result of this write. But they should still pay the cost of entering the condition for every thread and going through the motions and all the instructions in here. So that means that on a CPU, one of the straightforward ways to speed up a program is to add a conditional that avoids doing unnecessary work. But that doesn't really work on a GPU. All threads do all the work. So branching can be quite expensive. And there are other similar restrictions. You can't do recursion on a GPU because you don't really have a stack per thread. When you have 10 million threads, you don't really have room to give each of them their own stack. So there are some limitations there. You need to statically be able to bound the stack depth and all sorts of things. There are many restrictions that I won't be getting into. But just in order to explain to you just how nasty this programming model is and how uncomfortable GPU programming actually is, I will show you some examples which are quite simplified about how it works in practice. So, NVIDIA has kind of set the stage here. They're not the only providers of GPU programming, but everyone just copies their APIs now, at least in spirit. So the idea is that you launch something called a kernel function. It doesn't have anything to do with an operating system's kernel, but they just call them kernels anyway. And then you specify how many threads you want to run that function. And you do that by specifying how many work groups you want and how many threads belong to each work group. So work groups are kind of a scheduling unit. You don't actually have 10 million threads running on a GPU literally at once. You have some number of work groups where a work group is between 1 and about 1,000 threads. And then when one work group is done, it's stopped and another work group is switched in if there's room. And very importantly, communication between threads is only possible within one work group. So you can't just launch 1 million threads and have them talk to each other in all kinds of ways. You can only launch 1,000 threads and have them talk to each other, and you're still kind of slow. So as an example, this is how we might write a function in C to increment every element of an array by 2. This is, of course, in principle, a parallel operation, because none of these iterations of the loop depend on any of the other iterations. So we can turn that into a kernel function, which in CUDA looks a bit like this. This is just some junk to explain that we want to generate GPU code. And then for each thread, we compute the index of that thread by looking at the work group index and the work group size, and then our index within the work group. So that's just to compute the thread index. And because all work groups need to have the same size, we might actually have more threads than elements in the array. So we have to check, well, am I out of bounds of the array? If we're not, then we can perform an operation on the array element. And then this is just some GPU code. On the host, we need to manually allocate some memory on the GPU with a special function, and then we have to explain the group size, and we have to compute the number of groups so that we have at least one thread for every element in our array. And then we launch the GPU function with some magic syntax. But this thing that you have a separate pool of memory for the GPU that is different from the CPU, that's also kind of annoying. You have to manually copy back and forth. It's like an entirely different world. That has still gotten a little better recently, but it's still pretty annoying. Okay, so on one GPU I have at work, I could run that function on a 5 million element array in 189 microseconds. That sounds fast. It's faster than I can do it by hand, but the question is it sort of absolutely fast? I mean, how do we know whether this is a good program? And the way you usually do this on a GPU is that you measure how much memory you are moving per second, because most of the programs you are writing will be limited by how fast they can read and write in memory. So this program, it reads every integer once and then writes it back. So this is the formula for computing how the total memory traffic is 5 million times 4 times 2. And if I divide that by the runtime, I get around 200 gigabytes per second. Since this GPU has around 300 gigabytes per second peak bandwidth, that's not so bad, because peak bandwidth is if you really use all the tricks and cheat a bit in your benchmarks and all that stuff. That's what NVIDIA claims it can do. So that's really a hard upper bound. And the CPU only runs at 5.5 gigabytes per second, so it's significantly faster than the CPU, although you can make the CPU version faster as well. That program was not so hard to write. Sure, it was a little bit annoying that we had to allocate memory specially and write with some magic syntax and do some additional conditionals and compute thread indexes and all that, but it wasn't really so bad. So let's look at a more complex program. So what if we have a 2D array? Some people call it a matrix, and we want to sum every row in that matrix. First, we have to decide how to parallelize it. Let's just say that we launch one thread for every row, and then that thread just runs a sequential summation of the matrix row. That's pretty okay. Again, we're doing very little computation, mostly just reading memory, so it should be bandwidth bound again. We should see around 200 gigabytes per second. But let's check it. So with a 50,000 times 100 matrix, so 50,000 rows by 100, we can run that in 840 microseconds, and that is 22 gigabytes per second. That's really, really bad. I mean, we got 10 times as much before. And the problem here is that the way we access memory is not very good. GPUs have very, very fast memory compared to CPUs, but you must access it in just the right way, or you lose a lot of performance on the floor. Specifically, this GPU I'm using can load 384 bits in one cycle, but only if the addresses you are accessing in the same cycle are just next to each other. Otherwise, you will still transfer 384 bits, but we'll only be using 32 of them, and the rest will just be thrown away. So we are wasting at 9/10 of our potential bandwidth, which corresponds pretty well to how this program is 10 times slower than the other one. Specifically, we want what is called coalesced memory. So these are the memory access patterns we have right now. In all of the threads go through this sequential loop, and for the first iteration of that loop, thread 0 reads index 0 from the array. Thread 1 accesses index C, where C is the number of columns in the matrix. Thread 2 C. So that means that when the GPU dispatches a single instruction for all of these threads, it has to turn it into multiple accesses to memory. And that means we don't fully saturate the memory bus. Instead, we want it like this. So in the first iteration, thread 0 reads index 1, thread 1 reads index 1, and so forth. So that in the same clock cycle, neighboring threads are also accessing neighboring elements of memory. This really helps the GPU access memory much faster. And it corresponds to storing our matrix in a column major order. And this is exactly what you don't want on a CPU. So you need to do the exact opposite of how you would normally optimize for a CPU cache. So if we do that, that's not so difficult. I just change around the indexing in here a bit. Then we get a performance of 182 gigabytes per second. Okay, so we can do that. And that's actually in absolute numbers faster than our increment function, because we don't have to write as many results to memory. This runs in 100 microseconds, and the incrementer used 180 microseconds. But of course, now we assume that the matrix is stored in a column major form, not in row major form, which we can accomplish ourselves by transposing the matrix before we run our GPU kernel. So that's another thing that's usually necessary when doing high-performance GPU programming. You spend more time pre-processing your data and massaging it to get it into the exact right form for the GPU to run fast. And then the actual computation is pretty simple. Okay, but that's, again, some annoying stuff we have to do. But if we do the same transformation to our CPU implementation, then performance gets worse, because this is not cache-friendly indexing, but it is GPU memory bus-friendly indexing. GPUs have a small amount of cache, but usually you're dependent on access patterns instead of cache behavior. Okay, so that's a bit annoying. It means we can't just use the same code on the CPU and the GPU. But there's another problem. So we get pretty good performance when we have had 50,000 rows, because we have one thread per row. If we only have 5,000 rows, then yeah, okay, the absolute performance, absolute runtime drops, but now we only have 61 gigabytes per second. And for 500 rows, 7 gigabytes per second, and just continues dropping. And the problem is that this number out here is how many threads we are launching. So when we get beyond 50,000, then we have too few threads to saturate the GPU. So that means most of the GPU will just be idle, not doing anything, because usually you need around 50 or 60,000 threads to fully saturate a GPU. So to handle these workloads efficiently, we have to parallelize inside of each row as well. And this is where things start getting really uncomfortable. The way you do this is you do something called a segmented reduction, where you consider each row to be a segment, and then within each segment, you do a parallel reduction with a plus. So you sum each row using a tree reduction. This is in this simple example, we have 8 threads that each read an element from an 8-element array, and then neighboring threads communicate and combine their results, and then 4 threads, so we disable half of the original 8 and use 4 threads to combine their results and so forth. So you get this kind of tree where you can efficiently reduce an entire array to a single element. Of course, this only works if the threads can communicate, and as I mentioned, you can only communicate within a GPU workgroup, which has a static upper limit on how big it can be. But okay, let's just try doing that. So the way to communicate is to exploit another GPU architectural detail, which is that there are different kinds of memory. We have the global memory, which corresponds a little bit to our usual CPU RAM. You have a lot of it. It's relatively slow by GPU standards, but fast by CPU standards. And then you have this thing called local memory, which you have very little of, usually only about 64 kilobytes per workgroup, but it's very, very fast. And it's visible to different threads within a workgroup. So if you want to communicate between threads, one thread will write to local memory, and then another thread will read from local memory. That prevents you from going to global memory, which can be slow. And you use some barriers or thread fences to synchronize this access. There are no such thing as a mutex in the GPU. So I don't expect you to understand this and read it in detail, but this is a GPU kernel that is supposed to be launched with one workgroup per row in the matrix, and then within the row, all of the threads in the workgroup cooperate in reducing it to a single number, in summing it up. And if you really want it to go fast, there's lots of other things you have to do here, and you have to you don't need this barrier here if the threads are sufficiently close to each other, within 32 threads of each other, and all kinds of other nasty things, and you should probably unroll the loop as well. And in the end, this is actually the computation we care about. This is where we add 2 numbers. But the program just becomes swamped with all these low-level details about synchronization and communication. I mean, it's quite awkward. And with this simple implementation, while it does perform much better than our initial version, it still doesn't fully scale, and it's still much slower on the large data size than our original implementation. So this also shows another problem, which is that the optimal program depends on the input size. If we have a lot of rows, then we should use our original version with 1 thread per row. If we have fewer rows, then we need to switch to another version. So for efficient GPU code, you need to have to write multiple heavily optimized low-level implementations of each operation, and then pick between them at runtime based on the data you encounter. This, you will never want to do this. Nobody does this. It is extremely difficult. If you download NVIDIA's highly tuned libraries and you give them a weird workload with some strange sizes, then they will not run well. It's just too difficult and too time-consuming to write efficient implementations for every possible data set. So this is not just an academic problem. It really does. In principle, you can write all this code by hand. In practice, nobody has ever done it. So clearly something is not going well here. And when I encounter these issues, I'm always reminded of Dijkstra, my favorite grumpy computer scientist, who said in that the problems we have with machines are kind of proportional to the size of the machines we have. And he said we had gigantic problems back in 1986. So now we have machines 1,000 times as powerful. So Dijkstra's gigantic programming problem has become ours completely galactic scale programming problem. He also said something else, which is that the competent programmer is fully aware that he's really stupid. So we should not just treat this as a cool challenge in how good we are doing low-level GPU programming. We should really try to step back and accept that we are not going to be able to write this kind of code by hand. Because our brains are just not built for it. Human brains cannot reason about concurrency on a massive scale. We need some kind of abstraction that allows us to partition things and think about things in isolation. Specifically for GPU programming, we need a programming model where we can think sequentially. Things just happen one after another in a specified order, but permits a parallel execution. And it must be portable, because hardware changes. The stuff I told you about GPUs is true now. It might not be true 5 years ago, and it was slightly different. It might not be true in 5 years, and it was slightly different 5 years ago. And it must also support modular programming, because we want to be able to reuse our investments. So if you think about it, if I wrote a single GPU kernel for summing rows in a matrix, I can't just reuse that to sum the inner rows of a 3-dimensional matrix or something. All of these GPU kernels are fully specialized for their concrete domain and are not really very composable. So one thing that people hoped to do was to do really nothing. Just write code as they always did and hope that someone would write a smart enough compiler to figure out where the parallelism is. For example, if you just want to apply a function f to each element of some array and then write the results to another array, then yeah, a compiler can probably detect that this is parallel and generate parallel code for you, although it also depends on whether XS and YS overlap in memory. So it's actually, even this is just a tricky case. And it's hard for a compiler to detect that this is parallel. This one is completely impossible for any compiler I have ever seen to detect is parallel, but it is actually. And this is particularly tragic because many of the algorithms that we are using are actually innately parallel, but we write them down in these languages where we are forced to specify a sequential ordering of the operations, even if conceptually there doesn't have to be that much ordering. So these parallelizing compilers try to reverse engineer what we were thinking from the code that we actually wrote. And the question that I have to ask myself is, why are we not just saying exactly what we mean instead of first having to mangle it and specify it in a sequential way? So we need another vocabulary for programming. And parallel programming as a general problem is hugely complicated, and I don't claim to do anything to solve it in a general case. But for data parallel programming, there are some solutions that I think work well. So first, I need to emphasize that task parallelism, which is what most of you probably are most familiar with, is when you launch different threads that do completely different things, like in Erlang or in Go or whatever. And data parallelism is where all the threads do roughly the same thing. And this data parallelism is what I've spent most of my time on. And what is very nice is that functional programming, although not really renowned for being particularly efficient, actually has a vocabulary of bulk combinators like map and reduce, scan, filter, and such that can be implemented in parallel and can run very fast and do not specify any unnecessary ordering or dependencies. So instead of writing this loop, we just say apply the function f to the array xs and giving back a new array ys. This gives the compiler the liberty to execute this mapping in parallel. Similarly, this loop that I claim no compiler can parallelize on its own corresponds to another functional combinator called scan, which is a little more obscure, but is fairly well known in the literature. Of course, the problem is that modern functional languages are not really built for a parallel execution and are pretty slow and have other kinds and have support various features that you are not going to be able to support on a GPU, like high order functions or sum types or a lot of branching in general, recursion. So modern functional languages are not a good fit. So the good solution is to spend 4 years or more on co-designing a simple functional language and a very non-simple optimizing compiler that has a reasonable chance of turning a program written in a functional style into efficient GPU code. And that's the language Futhark that I've helped develop and design. So while I talk a lot about GPUs, Futhark is not a GPU language. It's a hardware-agnostic parallel language that uses functional combinators. The only GPU-specific thing about it is that the compiler we have written generates GPU code, but we just as well have written a compiler that generates efficient CPU code for multi-core CPUs. It's just not what we have done yet, because GPUs are a more challenging target and are, we believe, representative of the high-performance restricted chips that we will see more and more of in the future. It's not a parallelizing compiler. The programmer writes the parallelism, uses maps, reduce, and such things, and then the compiler just exploits the parallelism that the programmer provided. So I'll talk a little bit about the language properties that enable good generation of GPU code with some examples. So at a high level, Futhark looks like a least common denominator functional language. So you can define a function, add2, that takes as argument an array of integers of size n and returns an array of n integers and just applies the +2 function to each element of A with a map. And we can write a sum function that takes an integer array, returns an integer, and sums the array using this reduce combinator, which is also like fold in many other languages. And then we can write a function for summing the rows of a matrix just by saying map sum on this matrix. So apply the sum function to every element of the matrix. This is pretty straightforward. It's certainly much, much simpler and more high level than the CUDA code I showed you before. And it means we can reuse our significant investment in this one-line function when we're writing sum rows instead of having to rewrite sum from scratch. Probably not a lot of time saved here, but it sort of adds up for larger examples. Then we can compute an average by summing an array and dividing it by the size of the array, which is n. And then we have some function for constructing arrays from scratch. IOTA gives us an array 0 up to some number, and replicate just repeats a value in an array. And there's also some tactical sugar for sequential loops. So the language details at the level of syntax don't really matter that much. It's just every language is kind of weirdly subtly different from every other language, and Futhark is slightly different in some ways, but mostly really there's nothing unusual here for a functional programmer. So to show it a little bit, I'm going to discuss something called k-means clustering, which is an algorithm that is used fairly frequently in machine learning. So the problem is that we have some points in a space, and we want to divide those points into k different clusters, for here 3, for example, such that we minimize the distance from each point to the center of the cluster to which it has been assigned. Okay, so visually it's pretty easy to understand. It's just dividing some points. In the general case, it doesn't have to be 2-dimensional, but I don't know how to visualize a 27-dimensional space like this, so you get a 2D example here. The solution, according to Wikipedia, is to start by taking some initial centers randomly, then partitioning by associating each point with the closest center, and then you move the centers based on this new assignment, and then you just continue these two steps until you reach some kind of convergence. So what I will be talking about is this step here, where you are taking each point and you are constructing the average point for each of the clusters. So if we can do this fully sequentially by taking our array of points and their corresponding cluster assignments, just index from 0 up to k-1, and then we keep sort of a running and small array of the averages, and we just go through each element sequentially and add it to the corresponding cluster center. So right, this one is green, so cluster 1, so we put it in cluster 1 here. This one is 0, we put it on there, and so forth. Pretty straightforward and very sequential. We can write this in Futhark like this. First, we write a convenience function for adding 2 points, where a point is represented as an array of floating point numbers. So we're just saying take pairwise the elements of x and y and add them with a plus function. And then we can write this cluster means sec. Again, the specific details here are not so important, but the crucial thing here is that we have a sequential loop that just goes through all of the points and updates some accumulator with our running averages. So sequential and efficient from an asymptotic point of view, but this is of course not really what we want on a parallel machine, because there's no parallelism here except when adding these points, and that's not a lot. D is usually small, like 20 or 30 at the most. So this is not a good way to do it. So let's think about a fully parallel way of doing it, where we take each point and we construct a matrix that is all zeros except at the point corresponding, except at the slot corresponding to the cluster that the point belongs to. So we get this sequence of matrices, which we can then all add together, and then we end up with the final accumulator. We were by summing them in parallel at the end. This is basically just a map-reduce thing. So again, we define a utility function for adding 2 matrices, but the important thing is here, where we first construct the increments, which will be n matrices, and then after that, we do a reduction with the matrix addition as the operator. This is fully parallel, as we can get it, but it is not efficient. It has a different asymptotic complexity than the sequential version. This is O, K, and D, where the sequential version was just ND, I think, or was it? Yeah, ND. So this is perhaps parallel, but it's less efficient. So for large data sizes, this will actually be slower than the sequential version for sufficiently large data sizes. Clearly, that's not what we want. And the reason it's inefficient is that it is overly parallel. It totally maximizes all of the parallelism, but even a super parallel machine like a GPU has some upper limit of how much parallelism it can profitably exploit, and going beyond that is just overhead without any payoff. So we want to have as much parallelism as needed, but not more than that. This is in an ideal world, each thread will be assigned some piece of the total work, compute the results sequentially, and then all of the threads will cooperate in constructing a combined final result. But the specific number of threads to use varies from case to case and machine to machine, so it should not be visible directly in the programmer in the program that the programmer writes. They should be abstracted away. We want this. Each thread goes through some chunk of the input sequentially, computes a intermediate result, and then all of those results are combined in parallel. In Futhark, this is done with a novel combinator called a stream reduction, where we give it a function, matrix add, for combining per thread results, and then a function here, this is written as a lambda, that is run by each thread to compute a distinct result. And we just reuse our sequential implementation here. There's nothing fancy going on. And this also gives the compiler liberty. If it wants to fully exploit the parallelism, it will just make this chunk size 1, so each thread gets 1 element, and then all of the work is in the per thread combination. or it can fully sequentialize it by only launching one thread or however much, and giving it the entire input size. So we have written, as programmers, a high-level description of our algorithm that lets the compiler do the right thing, no matter what it might end up being. And that might also depend on whether this function here is called at the top level or deep inside some other function, where that already has a lot of parallelism on top. So this also helps modularity. And it really does work in practice. So on an NVIDIA Tesla K40 with on 10 million elements in a 3-dimensional space in 5 clusters, the fully parallel version runs in 134 milliseconds, and this chunked one in only 17.6 milliseconds. That's a factor of 7.6 difference. So this is significant. These are not small differences. Okay. I will say that Futhark is fast. I don't talk so much about what the compiler does to make it run fast, and it's kind of difficult to even explain what it means for a programming language to be fast. The usual way we do this is that we just take a bunch of programs written in another language that is acknowledged to be fast, rewrite them in our pet language, and then we see how fast they are. So we've taken a bunch of handwritten OpenShell or CUDA programs written by presumably expert programmers, although I'm like kind of skeptical myself, and then we port them to Futhark and see how fast they run. And these are some numbers based on implementations of the benchmark suite Rodinia, which is kind of a standard for this kind of work. The numbers show how much faster Futhark is relatively to the reference implementations. So we can see in many cases, even supposedly, and this is on 2 different GPUs, an NVIDIA and an AMD one. Even on things like this backcrop benchmark, which does the backpropagation stage of a neural network, the Futhark program is from 2.5 to 3.2 times faster than the handwritten code. And that is because GPU programming is so error-prone and so tedious that even an expert programmer trying to make things go fast will skip some things because they lead to unmaintainable code or are really hard to debug, or because they're just not worth it. And if you combine all of these small acts of laziness, then you do lose a substantial chunk of performance. But the Futhark compiler doesn't really know pain, and it's very, very patient, so it will do all these boring things for you. And it will also generate unmaintainable code, because the original code is what matters for maintainability, not the generated one. Of course, if you're really up against an expert programmer, like for this LUD benchmark, then they can't beat Futhark. It's just a compiler. A human can beat it. It's just that usually a human will not have the time or the inclination or the pain tolerance to beat it for many problems. So that's another question is it usable for anything? It's fast, sure, and I can write papers about it, but I really want to sort of make high-performance computing approachable to everyone, because I think it would be really sad if exploiting the parallel computers of the future is only for experts who can either afford to buy code written by experts or have enough time to become experts themselves. So the really nice division that makes it quite surprisingly easy to use Futhark is that there's this division between the CPU that sort of is in charge and controls everything, and then the GPU that does the work, and they communicate via some drivers and protocols. And what goes on the CPU is not actually critical for performance. It just has to send orders, data, and code to the GPU, which means that the Futhark compiler can generate all this controller code in a language that is not fast, but is convenient. Specifically, we've written a Python code generator. So we can write a Futhark program like this, it's called sumNats, that just sums the first n integers, and then we can compile it to a Python module, sum.py, that from within Python we can just import, and we have to instantiate it it creates a class that we instantiate so that we can do some bookkeeping of state. That's not so important. At the end, we have access to a method that takes an ordinary Python number as an argument and just returns a Python number as its results. Well, a NumPy number, but that doesn't really matter. The only difference from the point of view of the Python programmer is that this method will run way faster than any Python function he has ever seen before, because behind the scenes it will be offloading all the data and all the work to the GPU. So that works pretty well. Of course, summing integers is not very fun, so we can also do other things. For example, we could have Futhark return an array of color values that we can then blit to the screen using one of the Python libraries for that. And that's actually what I've done. This presentation is a Futhark program. And now it just turned every pixel into a particle that interacts gravitationally with every other particle on the screen, running on my GPU. So this is a pretty parallel program. There are tens of thousands of pixels, and they have to interact with all the other tens of thousands of pixels. So I don't think this would be able to run in real time, or almost real time on my CPU. But on my GPU, it works okay. And I can sort of make them go back to where they came from. So it works pretty well in practice. I'm pretty sure the slow part is macOS doesn't like the way I do my blitting, but that's not really Futhark related. Okay, so in conclusion, the future of computers definitely is parallel, and we cannot really expect people to write this kind of low-level parallel machine code that is required to fully exploit them. And the alternative is leaving computation in the hands of people who can afford to hire experts, or to just use libraries written by experts which are inflexible and limit what we do to the imagination of those library authors. We need programming languages that allow us to fully exploit these machines, and also to do pretty much whatever we want, write flexible software. As a technical thing, we need to be careful not just to over-parallelize. Even on a very parallel machine, there is a limit to how much parallelism is worth exploiting. Going beyond that limit just makes your program slower, not faster. And ultimately, this is about performance. There are already lots of very convenient, very flexible and powerful languages, but they're just too slow. So it's time to think about high-level, fast languages. Futhark performs okay, and it continues to get faster, as my real research is not on language design, it's on compiler optimization, so my job is to make this stuff go faster. The language seems useful. I've used it for some toy programs, and my friends have used it for some toy programs, and I know of some people in the industry who've used it for prototypes and things, because if you just want to see if a GPU is a viable option, then writing a Futhark program to get an idea of what is possible is much, much easier than learning CUDA and writing it all by hand. And everything is, of course, under a free software license and developed in public, and there's lots of other information out there. So that's my presentation. Thank you.
Are there any questions for Troels? No? Oh, you have one? Sorry.
Hi. I know approximately nothing about GPU computation, but I do have a CPU and a GPU. So,
Yes.
so what do I need, like to start? What other infrastructure do you rely on? So to speak?
So the biggest challenge is definitely you need working GPU drivers. Once you have that, most GPUs nowadays support an API called OpenShell as an open standard, and which is what Futhark targets. And it's generally surprisingly easy to set up. If you have a Mac, it's actually built in by default, it'll just work. If you have Windows, I hope not, but I mean, sometimes it will also have it just built in by default. On Linux, it's in all the package managers, the stuff you need. I mean, it is unfortunately more difficult than getting started on parallel CPU programming, but it's no longer as painful as it used to be. So if you have working GPU drivers, then the rest is pretty easy, just a matter of installing things.
Okay, so just the vendor drivers and Futhark.
Yes, so on NVIDIA you will need the proprietary drivers, unfortunately. Nouveau does not support OpenShell. For AMD, there is actually a fully free OpenShell stack now. It's not quite as fast as their proprietary stack, but it's very close, and it'll probably close the gap soon, which is very, very nice for me. Intel also has a surprisingly decent OpenShell stack on their integrated GPUs. They're much faster than people give them credit for.
Thank you.
Any more questions? Give Troels a hand. Thank you, Troels.